Okay, well, welcome to the final lecture of Math 307, Linear Algebra. We're going to be talking about the singular value decomposition today, and I'm going to level with you. I am a little bit sad because I just did this lecture and the recording did not save properly, so I'm recording this again. But what we have on the schedule for today is awesome. It is the apex of your learning in linear algebra. We're going to be talking about the singular value decomposition. So, remember in the last lesson, we talked about orthogonal diagonalization. That means that we have to start off with a symmetric matrix, and in order to be a symmetric matrix, that necessarily means that you have to be a square matrix. But when you're in that specific scenario, you're able to orthogonally diagonalize it, meaning that you're able to get a diagonal matrix with the eigenvalues down the main diagonal, and then an orthonormal set of eigenvectors that acts as our orthogonal matrix P. And so, the orthogonal diagonalization that we've been doing, as of last lesson, was A equals PDP transpose. Today, we are going to generalize this so that we're going to be looking at not just square matrices, not just symmetric matrices, but now we're going to look at any matrix A that's an m by n matrix. So we're looking at rectangular matrices today. These singular values are very related to eigenvalues. The singular values are the square roots of the non-zero eigenvalues of A transpose A. When you take A transpose and multiply it by A, it's a lot like squaring the matrix. And if you remember that, back when we were first talking about eigenvalue, eigenvector stuff, and we were talking about, difference equations and differential equations, all that kind of stuff, we were taking powers of matrices. And the eigenvalues of the matrix A squared are the squares of the eigenvalues of the matrix A. And so we've got something very similar going on here with A transpose A. It's a lot like we're working with the squares of eigenvalues of A. But again, A can be a rectangular matrix, so proper eigenvalues don't even really exist for this thing. Eigenvalues are really only defined when we're working with square matrices. So singular values are kind of the closest thing that we can get in this context to eigenvalues. There are three major matrices that appear in the singular value decomposition, just like the PDP transpose that I wrote up top earlier. Here we've got a matrix U, a matrix sigma, and a matrix V transpose as our decomposition of the matrix A. U is an m by m orthogonal matrix whose columns are eigenvectors of A transpose. So you multiply A times A transpose, you find the eigenvalues and eigenvectors. U is all of those eigenvectors. V is all of the eigenvectors of A transpose A. Do notice that U and V are different sizes. They're both square matrices, but they're different size square matrices. And sigma is the rectangular matrix that has the same dimensions as the original matrix A. And that has, it's a lot like the matrix D in the orthogonal diagonalization, because the singular values are on the main diagonal of this rectangular matrix. So yeah, it's very, very similar to what we've done with orthogonal diagonalization, except in this case, we're kind of making the best with what we're given. And, in order to come up with the matrices on either side of sigma, we're having to find eigenvectors of A transpose or A transpose A. The nice thing about that is that both of those matrices are symmetric, and it means that their eigenvalues are going to be positive. So yeah, A transpose is a symmetric matrix. A transpose A is a symmetric matrix. That means that we're going to be able to orthogonally diagonalize each one of those. And that's where we're, building off of the orthogonal diagonalization from last time. We haven't proved it yet. I will show this proof as I'm ending the video. But yeah, both A transpose A and A transpose have the same non-zero eigenvalues. That's handy, because it means that we're able to use those, in both instances. Let's look at our first singular value decomposition. We have our matrix A. We take the products A transpose and A transpose A. Those give us two square matrices that should have the same non-zero eigenvalues. Both of these matrices, these square matrices, are rank 2. We started off with a rank 2 matrix A, and so we're not going to be able to, improve upon that rank when we're multiplying A transpose times A. And so the thing is A transpose A, A transpose, the first one, is going to have two eigenvalues, 16 and 6. The larger one, the 3 by 3 matrix, is going to have three eigenvalues, 16, 6, and then 0. Since A transpose A is a 3 by 3 matrix that is rank 2, it necessarily means that that matrix is singular, has a 0 determinant, all that good stuff. And so, its third eigenvalue is 0. Once you find the eigenvalues, and here we just use the smaller matrix because that one was easier. Once you find the eigenvalues, you want to find the eigenvectors. What I would suggest to you is use the eig command on Octave to find these things, at least to check yourself when you're doing these. There's going to be one of these problems on your final exam for actually doing a singular value decomposition. And I would certainly encourage you to use Octave to at least check your work along the way. You will probably have to do a combination of Octave and your own handwritten work because you want to make sure that you get the square roots correct as you're working along, and as you're normalizing things, you want to just make sure that everything's the way you want it and the way that you understand it. But the next stage here after finding eigenvalues would be finding eigenvectors. Here I think we find the matrix V, which would be the eigenvectors of A transpose A. And again, you just solve the system, you find the null space of A minus lambda I, basically, we've got A transpose A here. But, you're solving for that null space to find a basis for each eigenspace corresponding to the different eigenvalues. Here we've got 16 and 6. On the next slide, we've got the eigenvalue 0. And so each one of those has a one-dimensional eigenspace, which is cool. We do know that eigenvectors that come from different eigenvalues are already orthogonal to one another. And so the biggest thing to do now would just be to normalize all of those eigenvectors so that you get the orthogonal matrix V right there. everything is, yeah, orthogonal and normal, we're great. Honestly, I would do the same exact thing for the matrix AA transpose to find the matrix U. Here, they describe kind of a little bit of a shortcut to get the matrix U. What they're doing here is recognizing then that when you start off with the decomposition, A equals U sigma V transpose, and you multiply on the right-hand side by V, you get AV equals U sigma. And then you're able to use some algebra to find out what U1 and U2 are, the columns of U. Honestly, though, I would just find the eigenvectors of AA transpose the way that we normally do. Just looking at the null space of AA transpose minus lambda I. But yeah, once you have all of those, oh, now here's my writing from last time. Sorry, I thought I scrolled through this and I thought it was all gone. It's too confusing to see all of that at one time. I'm going to erase it and do it again. Okay, so initially down here at the bottom, we have the singular value decomposition, where we have our matrix U here out in front, our matrix sigma, that is a rectangular matrix with the largest singular value up in the top left-hand corner, and then we go down from there. And then this one is V transpose. The green writing that you see up above is one of the coolest things that we can do with the singular value decomposition. We can express a matrix A as a sum of rank 1 matrices. And the first rank 1 matrix that you make is the most important in a sense. So what we're doing is, yeah, kind of picking out the most important parts of the matrix one by one. So, for instance, for this first green matrix, what we're doing is we're taking the first singular value, 4, and then we're taking the first column and the first row. And what we're doing is an outer product, really, where we use that column vector and row vector to create a 2x3 matrix. And the calculation's right here in blue of what that looks like. But yeah, we end up getting a rank 1 matrix, 2, 0, 2, 2, 0, 2. And this rank 1 matrix is, in some sense, the best rank 1 approximation of the rank 2 matrix A. So yeah, A has more information contained in it than, you know, this new matrix in blue. And one way to look at this and, you know, understand what does it mean to be the best rank 1 approximation is, let's look at what happens if I treat all of the rows of these matrices as vectors, and we go to GeoGebra, boom. Of course, it's been long enough that GeoGebra has forgot that I used it. Here we go, let's open this up. Here, U and V, the black vectors, are the rows of our matrix A. And if I were to frame the problem as, hey, you have these 2 linearly independent vectors worth of information. What if I said, ooh, 2 different vectors, that's too much information to keep track of. Can you give me one vector that, kind of summarizes them both the best? Well, enter vector W. W is kind of like the average between the two, and it is the row in that first rank 1 approximation of the singular value decomposition. Yeah. And so, thinking about this like rank 1 approximation is maybe not super, I don't know, useful at this stage because we're dealing with really, really, really small matrices. But for our project, we're going to take a picture, and that picture is going to be, a grayscale picture, maybe roughly 1,000 pixels by 1,000 pixels, so that you get a 1 megapixel picture overall. So 1 million pixels. We can use Octave to read in an image, and if it's in black and white, if it's in grayscale, then each pixel gets a value between 0 and 255. I think with 0 being probably black and 255 being white. But yeah, each pixel would be its own entry in a 1,000 by 1,000 matrix. Now, since we're using the singular value decomposition here, we don't necessarily have to use a square picture. We could use a rectangular picture, and that is fine. But essentially, when you read an image, you get a huge matrix that, maybe has 1 million entries in it. The singular value decomposition can be really nice for compressing this image, or, getting the most important features out of an image without actually keeping all of those individual entries. So a rank 1 approximation of an image would be pretty garbage. That means you'd have 1 column vector's worth of information, 1 row vector's worth of information, and 1 singular value, which basically means you'd get, I don't know, like a set of streaks that are of various shades of gray. But in the 1,000 by 1,000 context, it is possible to get a pretty good image, maybe just looking at the top 30 singular values. And that would represent a really large amount of savings in terms of the storage that you would have to do, or possibly the speed of a computation that you would need to calculate based on an image, if we're able to compress all of this information down. So instead of keeping track of 1 million different values, maybe all we have to do is keep track of 30 column vectors, 30 row vectors, and 30 singular values. And then we would be able to get a picture that, while it might look a little bit more grainy than the original, would have the most important parts. And actually, I'm not sure if this is still part of the technology, but early on, that's the kind of stuff that they would do to get pictures on ultrasound machines. You know what an ultrasound machine looks like? I mean, or an ultrasound picture looks like? It's normally grayscale, kind of blurry. Yeah. Imagine that kind of picture going on when you're thinking about the singular value decomposition. What's happening is, you're peeling off kind of the most salient, rank 1 matrices to combine together to actually approximate the original picture. And yes, that saves on storage and saves on speed when you're able to implement that correctly. Okay, so that's a big reason why the singular value decomposition is important. Is because we can use it for really cool approximations. You can use it in data science to kind of pull out the most important properties of a group. You will see that on our playlist, I have included at least 5 different videos relevant to the singular value decomposition. One is from a professor at MIT who'll just give you another perspective on, all the different matrices, U, sigma, and V. Does a good explanation of that. There is another video from Stanford where he actually explains the singular value decomposition as related to like surveying movie watchers, and you're able to, using the singular values, kind of group different users based on their interests. And so the singular value decomposition can be used in data science. There's another video from 1976 that talks about how the singular values were calculated on computers at that time, and has some engineering stuff in there, it's a funny video to watch. And then there's another one or two that include dragons and the singular value decomposition, which is, it's cool. So go ahead and watch those other videos. They give you different complementary views of what the singular value decomposition can be used for. Anyways, I'm going to try to get back on track. I think maybe we'll go through another example, maybe 2, but probably just one more example of doing a singular value decomposition. Before I go, do know that there is an octave command for the singular value decomposition, and I'm sad that that just happened. If you start off your command like this, where there's a space in between U, S, and V, I'm using S for sigma. The lowercase svd command will give you the singular value decomposition. It'll give you 3 matrices, U, sigma, and V. Do recognize that this V is not V transposed. In order to get V transposed, you need to transpose V. But yeah, that's the octave code in order to get one. The downside of using octave is that you're going to get basically decimal approximations to the exact values. And so, still working the stuff by hand, at least for your, final exam, will be somewhat necessary in order to get the exact values, because they're going to want you to put in like the square root of 6 or the square root of 2 actually into your matrix online. But yeah, that command for finding the singular value decomposition is super useful. All right. This one's a column vector, and this one's interesting to look at because you get a very lopsided singular value decomposition. The only non-zero eigenvalue in this case is 3. And, this kind of shows you that once you find the eigenvector corresponding to 3, when you're looking at AA transpose, you could solve the system like you normally do, and that's what I would suggest. Here they just kind of, instead of solving the system for the null space, here they just add on basically I hat and j hat onto the original vector, and then use Gram-Schmidt orthogonalization to come up with a basis for R3. Anyways, I don't want to waste too much time on that, because those 2 other eigenvectors that they find that correspond to the eigenspace for 0, lambda equals 0. When you look at the entire singular value decomposition, those two columns aren't even going to really factor into the computation, because the last two columns of U get multiplied times the zeros in sigma. But yeah, you can see how that is a singular value decomposition of that original column vector A. Yeah, that's just a rank 1 deal there. Here's a 2x2 thing. Yeah, you can see right off the bat that one of these columns is a scalar multiple of the other. That means that one of our eigenvalues is going to be 0. And all of the writing that you're going to see here, I might have to erase some of it, but it is explaining how to you're able to see all of the 4 fundamental subspaces of this original matrix A based on the singular value decomposition. So yeah, when we find the singular value decomposition for this, we're going to find one non-zero singular value, and then we're going to have 0 as the other one. And you're actually able to find bases for the column space, the row space, the null space of A, and the null space of A transpose within the singular value decomposition. It is theorem 8.6.2 in our book. That's why I wrote that there the first time. But yeah, basically the column space and row space, those vectors are found in U and V respectively. And those ones correspond to the non-zero singular values, whereas the null spaces of A transpose and the null space of A correspond to the 0 singular values. And so yeah, what I did here at the bottom was just show that the vector -4, 1 was indeed in the null space of this original matrix A. Yeah, they made a mistake here in their singular value decomposition, and I think they wrote V instead of V transpose. But yeah, you can actually find bases for all of those 4 fundamental subspaces of A, which I think is really cool. Just coming from the singular value decomposition. And then that's it. Honestly, this one is just more of the same. If you want to look at a really nicely worked out example in our book, 8.6.1 is a good one to look through. This is the ending slide. It shows you that A transpose A and AA transpose have the same non-zero eigenvalues. I'm not going to dwell on that too much. I do want to encourage you to watch those other videos about the singular value decomposition, because they are enriching and they're going to make as much, if not more, sense than what I just did. So yeah, please watch those videos. We're going to be working on our singular value decomposition project for the next few days. Ideally, that would be done towards the beginning of next week. And you'd then be able to work on your final. There are 10 problems in your final. The singular value decomposition project hopefully shouldn't take too long. It kind of depends on how familiar you are with Octave at this point. But yeah, do realize as you're working on this stuff, please ask for my help. I will be lurking around on Pronto, and I would be happy to chat about any of this stuff in the coming days. Um, but yeah, that's going to be it for our class. This is the last lecture. Um, and we have the SVD project and our final exam, which is 10 questions. I think you guys are going to be able to handle this. It'd be great if everything was finished up by next Friday, but if we need to extend into finals week, that's okay. Just please stay in communication with me if you need extra time. So I think that's it. The video should be showing up here, and I will see you on Pronto. Thank you for listening. Bye.